Now I'm going to talk about one of the most basic tests of inferential statistics, which is the one-sample z-test. Remember that the empirical rule tells us what proportions or probabilities are associated with different areas of the normal curve. Basically, we know that 68% of scores will fall within one standard deviation, and 95% of scores will fall within two standard deviations, and so on. So, using this information, we can answer different kinds of questions, and here's one example. In the population, the average IQ is 100, with a standard deviation of 15. A team of scientists wants to test a new medication to see if it has either a positive or a negative effect on intelligence, or no effect at all. A sample of 30 participants who have taken the medication has a mean of 140. Did the medication have any effect on intelligence? Now, in this example, realize that we know the population standard deviation, which is 15, and we have a large enough sample size. In this case, it's 30. Because of those two pieces of information, we're going to do a z-test. If we didn't know the standard deviation of the population, we would actually do something called a t-test, which I talk about a little bit later. So, notice where I put the blue area. We would expect the mean of most samples to be pulled towards the center. In this case, it's 100. But imagine if we had something that was like way over here. If something is so unlikely to occur by chance, we can conclude that it occurred for a reason. In this case, if we calculated something that was so unlikely, we would conclude that our medication had some kind of effect on the sample mean because it is so different from the population mean that it's almost not impossible, but it's incredibly unlikely this would have occurred unless we did something to change it. So here's our example, and there are 6 main parts to doing this test. It might be different depending on your teacher or class, but just realize that by doing these 6 steps, we'll get to the same rule and go through all the same processes. First, we're going to define our hypotheses. Then we're going to state our alpha level. We're going to state our decision rule, calculate the test statistic, state our results, and then state our conclusion. So the first part is to define the hypotheses. In this case, our null hypothesis is that the population mean is 100, and our alternative hypothesis is that the mean is not 100. I did this because in the sample realized that the population mean is 100. That means that we expect the mean, we expect our null hypothesis to be 100. And the alternative is that it's any different, either intelligence was lowered or if intelligence was increased. Basically, our alternative is we're testing to see if it's different than the expected population mean of 100. So that is step 1. Now, step 2 is to state alpha. Remember that alpha is our probability of making a type 1 error. And in this case, we're going to set it at 0.5. It'll almost always be set at 0.05 at default. It might be 0.01, but in this case, we're just going to use 0.05. So the next step is to state the decision rule. Now, this is going to be a two-tailed test, which I've talked about before, because IQ can either be lower or higher than 100. So that means we're going to split that 0.05, that 5%, into 2 halves, where if anything falls within the 2 rejection regions that are marked by the 2.5% probability, then we can conclude something. So what z-scores are going to be associated with those 2 spots, because this is a z-test after all? So we have to look at this. Now, if the area in the tail is 2.5%, we know that the area in the body is 97.5%, and the z-score associated with that is 1.96. This is just taken from my standard z-table, which you should have. So I'm going to put that at the bottom of the table. So we know that we would expect most means to fall within negative 1.96 and positive 1.96 standard deviations from the mean. So if the z that we calculate is less than negative 1.96 or greater than 1.96, we're going to reject the null hypothesis, because if it falls without that range, we can conclude that this is an unusual event, and that is probably because of the medication. Now, step 4 is to calculate the test statistic. Basically, we're going to calculate the z. And we're going to use this z-score equation, which is the same as it has been before, except now we have an n because we're going to consider our sample size. So what I'm going to do is put things in there. The x bar, our sample mean, is 140. The population mean is 100. The population standard deviation is 15. And the size of our sample is 30. So when I put all those things in there and solve for z, I end up with a z of 14.60. So now we can go on to step 5, which is state our results. Remember that our decision rule was, if z is less than negative 1.96 or greater than 1.96, we can reject the null hypothesis. And in this case, our z was 14.60. Now 14.60 is definitely greater than 1.96. So we can reject h0, and by rejecting the null hypothesis, we're saying that we accept the alternative, basically. We're saying the alternative is true. We're saying that there is a difference, that the sample mean is not the 100 it was expected to be. So as for our conclusion, we can say that medication has been significantly affected by intelligence. And that last part there is actually how you will officially write what that is. It'd be z equals 14.60, probability less than 0.05, significance less than 0.05. You don't really have to include that last part unless you're asked for it, but realize that the last part, reject H0, was our result. And this part, medication significantly affected by intelligence, or rather the opposite, intelligence significantly affected by medication, is our conclusion. And that is a one-sample z-test where we use things like null and alternative hypotheses. We came up with a decision rule, calculated the test statistic, then found our results and our conclusion.